Right, good afternoon, everybody. Welcome to our QBEST Energy webinar. It's the Queensland Business Energy Saving Transformation Program. That's what QBEST stands for. My name's Andrew Chamberlain. I'm the Project Manager for Energy Projects with Queensland Farmers Federation, and I'm joined by Jonathan Mendez, who works at QFF on QBEST and EnergySQ programs, and also our presenter Ryan Dillon. So it gives away, guys. Thank you. And also we've got a special guest, Andreas Jaramillo, who was working with us on QBEST up until recently. So welcome, Andreas, and I can see we've got a couple of other people joining us as well. So welcome. Just a couple of little intro notes. We've set it up so that people are muted and their cameras are off, and that helps with people in regional areas with their bandwidth and everything. So if you do have any questions or comments as we go, you'll see at the top there's a Q&A button, and you can click on that and put a question in there, and we'll put those questions to Ryan before the end of the presentation. We are being recorded, so this presentation will be recorded, and we'll put it on our Queensland Farmers Federation YouTube channel and the Ag Energy Hub website when the program's been finished, when the webinar finished, so people will be able to watch it. So any comments or questions you make, we'll answer, and they'll be recorded on that video forevermore too. So welcome everyone. It's great to have people on board, whether you're watching this live or watching it later on the Queensland Farmers Federation website. Just a really quick intro from me. Then we're going to have a 30-minute presentation or so by Ryan Dillon from Websters Group, who's been doing some of the energy audits for QBEST for us. We've got plenty of time for questions and answers at the end, so please feel free to put them in that, either the Q&A tab or the chat tab, and we'll make sure we get to them before the presentation's finished. And then I'll just have a couple of quick next steps at the end of the presentation. Just a really quick summary of the Queensland Business Energy Savers Transformation Program, QBEST. It's a program that we run here at QFF in partnership with the Queensland Government's Department of Energy and Public Works. We're delivering 35 Type 2 and Type 3 energy audits on farms throughout Queensland, and we're making the findings from those, as well as all our previous energy programs, on the Ag Energy Hub website, and I'll give you a bit of an intro to that at the end of the webinar. And also I'll mention farm energy efficiency rebates. They've closed at the moment, but we'll keep people updated through the Ag Energy Hub website when the next round of those is available, or any other energy efficiency rebates that are put up from time to time. Just a really quick intro about Ryan Dillon. I'm going to cut straight to the presentation here. Ryan Dillon is the Managing Director for the Websters Group. Websters Group have been involved with a lot of energy audits that we've done through the various programs we've managed here at Queensland Farmers Federation, and even before that with Ergon Energy, and also Ryan worked directly with Growcom, or the Queensland Fruit and Veg Growers, on some of the audits that they delivered on previous programs as well. He's done 3 recent QBEST dairy audits, so we thought this would be a really good way to summarise some of the findings for those for dairy farms. Recently, he was a runner-up in the Energy Efficiency Council Awards for the Best Ag Energy Efficiency Project, and that was for a project he delivered on one of the previous energy efficiency programs that we've run. We've also got a story on our QFF website, energy audits and jelly beans. There's a webinar that we'll put a link to on that too, where Ryan delivered to Growcom a jelly bean for every $100 in annual savings that were found through his energy audits. So welcome, Ryan.
Thanks, Andrew.
Unmute yourself. I'll unshare my screen, and but firstly, thank you very much for your time this afternoon, and we look forward to seeing what you can tell us about energy efficiency in dairies.
Yeah, thank you, and welcome everyone. Is my screen fully shared there, Andrew?
Yes, but I can see my slide.
Great, fantastic. So dairy energy efficiency and auditing to the Australian standard. Now, when you'd mentioned QBEST before, the T for transformation is really striking in that it's quite remarkable what actually is possible in regards to energy and cost savings once you implement the recommendations, having gone through what is really quite a detailed process through an Australian standards energy audit. So as you can see in the chart here, that
Ryan,
initial,
it's
yes?
actually showing your screen with one of my slides on it. So you might
Okay,
need
my apologies.
to unshare and reshare.
Sure, let me just fix that. How about that now, Andrew?
Yep. So you're up to the 30% to 50% slide.
Great. So picking up on that, transformational energy efficiency gains really are possible after a type 2 energy audit, where that first initial 30% is achieved through a combination of efficiency and renewables, where a further 20% is possible over time. So thinking transformation, thinking grower benefit with energy as one of the top concerns and highest costs among with labour and other input costs. Imagine having your energy bill, say it's 20 grand a month, cut down to 10 grand a month. It's possible, and we're seeing case studies with this order of magnitude in certain instances, although it does require some effort and it does require that really granular look from an audit perspective. Now, this is an example from the United States, from the Lawrence Livermore National Laboratory, where on the left-hand side, we have energy generation, so wind, gas, coal, nuclear, solar. This is whole of economy energy generation, and in the pink squares on the right, what that energy powers, so residential, commercial, and industrial. Now, the quick summation of this chart is that there's a significant amount of energy on the left, and on the right-hand side, we have in the dark grey what we call energy services, and in the light grey, what's rejected energy, or essentially waste. And the key message from this chart is that in this case, across the entire economy in America, 1/3 of energy actually provides a relevant use or function or service, provides the work that a motor provides or the refrigeration that a dairy milk fat uses to chill milk, and the rest is rejected energy, which is predominantly simply just waste or heat. So coming back to this example, it isn't a surprise that at a site 30 to 50% is possible as a cost reduction, because we just quite simply waste so much and energy efficiency hasn't really been implemented to scale, and there's still a significant opportunity. So what I wanted to draw into today, thinking about that chart, there has been quite a push towards renewables and the supply side. So simply connecting solar energy, implementing rooftop solar for dairy farms. What role does energy efficiency have in actually optimizing the waste, reducing the waste first, so that then you can implement a solution and achieve a higher return on investment? So the problem, or the case study we're addressing today, is through the program, we had a dairy farmer that initially signed a contract and paid a 50% deposit for a $330,000 200 kilowatt system. The question or the opportunity through the program was, is there a better return on investment by investing in an energy audit, optimizing the site through energy efficiency, and then installing solar? So sustainability or energy is really data-driven and evidence-based. We use a lot of tools in energy auditing, thermal cameras, energy data loggers, digital tachometers to effectively measure. With the adage, you can't manage what you can't measure. Also in this case study, and quite commonly with other dairies, we have motor runtime counters. These are devices that are installed for about a month, and they give you at a 1 second level of interval exactly when every motor is turning on and off. So we then look at this data, and you can see here, this is an average dairy. At 6 a.m, you've got the morning milking, big spike, afternoon 5 p.m, the afternoon milking, and another spike there. We want to understand exactly which motor turns on and off and when, to be able to build what's called a time of use profile, where we really analyze everything. And as an analogy, if you think of an accountant preparing a profit and loss statement, we're almost preparing a profit and loss for each individual motor. We develop a full schedule. We identify not only the annual energy consumption, but within every hour, what that motor is actually doing within the 1 month typical sample period. So it's a lot of data. Just a quick screenshot for the 1 month in this case study at a 1 second interval. It's 41 million different points of data. So from a grower perspective, why do we have to have so much detail? Well, the devil really is in the detail. Here's an example of where we attach this motor runtime counter to a pump. Now this pump we found through this 1 second interval monitoring was turning on and off every 30 seconds. And we wouldn't have seen that in the 30-minute interval data from the main meter, or if we hadn't focused on the devil being in the detail. So this pump's turning on and off every 30 seconds. And in this instance, the pump actually is for a storage tank, and the storage tank's filled by a bore pump. So in the annual energy balance, you would see a segment that shows bore use, but on a daily profile, here in green, we actually see this bore pump. Now it's running 24 hours a day, and if we hadn't attached the motor runtime counter, we mightn't have been able to detect this. But in this instance, as you can see, that's a $20 standard timer. We turn off the pump that's running, that's basically just feeding a leak, an underground leak in the supply pipe work. And 50,000 kilowatt hours a year later, and $13,200 worth of savings just for a $20 timer, because we monitored and went to this level of granular detail. And it's effectively exposing things that might be invisible. And thinking back to this chart, looking at an economy-wide scale, with 2/3 of energy being generated ending in waste, across the economy, this is hundreds of thousands of pumps, motors, and things doing similar things, turning on and off, not providing any functional service that could otherwise be improved, where this is really definitional energy efficiency type of interventions. So aside from monitoring devices and usage patterns, we also use thermal imaging to try and identify problem areas. Now, this is the refrigeration compressor and condenser that chills a milk fat. So the cows are milked, goes into a milk fat, it's refrigerated to 3.5 degrees. This provides that refrigeration work, and looking at it, you might not think anything's wrong there. But when we put a thermal camera on it, you can actually see, particularly in the picture in the top right-hand side, the wall behind that condensing unit's quite warm. And while to the untrained eye, that might not seem like much, just in that picture there, what we can actually see is that the air rejected that moves out to the right-hand side is hitting the top of that roof. And this is this little red chart on the picture on the right-hand side, where we see by the shape of the roof, some of the hot air rejected is actually recirculating and being sucked in by the back of this condenser. So what does that mean? Well, we put a digital temperature logger with a 1 second interval, and it's calibrated. It's about $400 as a sensor, so it's a precision instrument. And we're monitored just 2 feet apart the ambient air. And then we're looking at the recirculating air just in the square on the picture on the left to give you an indication of where we put the 2 sensors. And comparing the temperature of the air that gets sucked into the condenser versus the ambient air, what we're seeing is a difference of above 10 degrees Celsius when the milking's occurring. So in farmer language, or in layman's terms, it's sucking in its own juice, it's rejecting this air, and it's similar to running the system in winter as if it was summer. Now, while we're going quite technical here, another indication might be the fact that on a really cold winter's day, the cat's hanging out up there, and it's really warm, like you can physically feel it. And this air is basically just hitting this roof, recirculating back into the condenser. Nice, cozy environment, but not good for the energy bill. So thermal imaging helps identify these problem areas with further analysis with temperature data loggers. In this instance, it was a quick intervention, raise the roof up by 2 foot, move things around so you can save 15,000 kilowatt hours a year, or $3,200 in annual cost, simply by not recirculating this heat because no one's probably ever checked it, and the original installer might have done so when energy was cheaper. Some of these things are increasingly more important given the significant increase in the cost of electricity. And it's not only the amount of electricity that's consumed, it's also what we call the peak demand. Now, at this dairy site, we had a peak demand on the 15th of May of 120 plus kilowatt hours in that 30-minute period of which you get charged. So it's not only the area under the chart or the cumulative energy use, but also how spiky the chart is, where with ergon or tariffs within other retailers and also across Australia, a move to cost-reflective pricing where you're charged for the peak demand is a constraint on growers and something they need to get their head around and develop solutions for. So this time of use balance in an audit helps not only identify the bulk efficiency, but also time of use efficiency, which is really key. And using that analogy of the profit and loss statement of the cost of every motor, we're looking at putting in Fluke 1738 power loggers that have amps, volts, power factor associated with every motor. So in that profit and loss, energy accounting, developing a balance sheet for what your liabilities are from an energy cost perspective, we find the outliers. We find what isn't working. We find what could reasonably need to be recommissioned or what's contributing to peak demand. And it also helps us prove things outside of the audit sample period. So in this instance, there's two barns here. The cows actually come in and there's 18 fans per shed and they're 3.2 kilowatt nameplate rated fans. So a significant energy use, and it's visible within the summer energy billing. But we use this metering to actually test the fans in the audit methodology. So in this instance, you can see there's on the right-hand side, here's the fan here, if you follow my cursor, and there's a number of fans all the way back through these sheds. So we tested those, and there's a speed controller associated with these fans. So in this instance, when they're at full speed, each barn used close to 50 kilowatts. I'd mentioned peak demand, quite often measured in kilovolt amps, and the power factor for those energy nerds was 0.95. And as you reduce the speed, the power factor dropped, which means proportional to the kilowatt demand, the kVA instantaneous demand increased. So what you're seeing in this scenario is an interesting discussion with a grower or a farmer. Hey, do you want to reduce your fan from speed 6 to 5? Did you actually realize that just reducing it by 1/6 in this instance, based on the configuration, almost cut the energy use in half? Now, having this attention to detail and this granular focus reveals things. And I think we visited site around 5 or 6 times, and you don't find everything on the first visit. So something that popped up to me in this testing was that the wiring is up and down the purlins of the shed, so that you've got here, because it's naturally how you'd wire a building, just cables running that. So all of those fans are turned on at once, all those fans are turned on at once, all those fans are turned on at once. Now, if only half the cows are in the front of the shed and say they're just all up here, you've got to turn all the fans on at once. And we're thinking about installing a switch, but that would only switch on, in this instance, either the left, the middle, or the right-hand side set of fans. We can't really break it up into zones. So we had some quotes and we looked at the ability to actually create zones. And aside from adjusting the speed, there's less cows in there. We don't need to run all the fans at once. So significant energy savings. Further to this, with the time of use profile, we actually identified some switching logic where we just have the fans turn off if they're on within the milking. So I'd mentioned on the 15th of the 5th, the peak demand was 120 kilowatts. If you had that switch in that automatically switches it off, say for a 2.5 hour period, we wouldn't have at speed 6 another 50 kilowatts on peak demand, creating an extra peak demand charge. So the savings just from the zone intervention, 33,000 kilowatt hours a year, or 11,500 in annual cost savings. You add on some of these timing benefits and the savings are quite significant. Something else that's significant in dairies is hot water use. So hot water use is actually a really simplified form of energy. Thinking back to that chart of that whole of economy use of energy, we can see that with 2/3 of it being waste and that predominantly being heat, how do we actually use waste as a resource to generate hot water, given it's a very simple form of energy use? It's either an element heating up. How do we capture heat? How do we reuse heat? How do we think from a systems perspective? Where am I wasting heat? Where can I reuse it to fill this larger electrical energy use in dairies? So when you actually take a systems thinking approach, think of what's used what and where and when. Through this, we identified refrigeration compressors rejecting a significant amount of heat. And in this case, you're actually able to install a inline hot water system that recovers heat from the condenser. So the condenser is that big fan in that shed that I showed with the cat. That's using fans to put heat against a set of aluminium heat exchange units and reject heat to the atmosphere. Why don't you just reject it to water and have air to water and use that cool water to cool the system, effectively obtaining free energy? Now, there's a caveat to that where there's a small amount of energy use associated with running the condenser, and I won't go into the explicit details, but it's effectively free energy and it's recovering that waste heat. So thinking about systems, how do you audit the system and match those losses to potential end users and use creative opportunities to recover waste heat? And in this instance, the savings were significant, with a forecast 34,000 in annual kilowatt hours avoided, and that comes with 7,100 in annual savings. When you're monitoring a lot of things within a dairy, I think there's a really important adage again: you can't manage what you can't measure, and that relates to just business in general. So here we had monitoring of the water in the cleaning lines, or the lines that transfer milk are cleaned. And we can see here that on the bottom around here is the ambient temperature of water as you're flushing those lines. And these spikes are when you actually put that 60-degree water through the milk lines to clean them. So a non-energy benefit that tells you how's the site running, is it not only efficient, but is it running as you expect? You can actually see here, you're supposed to have 2 cleanings, one after each milking. And in this 2-week period, they missed cleaning the milk line. So the farmer wasn't actually aware of this. And then it talks to, hey, we need to retrain and educate staff. This is the quality control issue. We're penalized for bacterial loads. It's a safety concern. Not only do we need to be energy efficient, but this data is really invaluable in finding a whole raft of other components to look at that would call non-energy benefits. So what does this all mean? Here's a quick summation of the annual energy reductions we're able to achieve through these different creative or data-driven interventions. On the left, we have the vacuum pump. That already has a variable speed drive, and that was found to be efficient. The milk vat cooling, you can see here in the blue bar chart component, that's the current use. Now, once we rectify that roof, this is the forecast reduction in use. So you can see there's a significant reduction in milk vat cooling simply by lifting the roof up a couple of meters, recommissioning the system, making sure it doesn't suck in its own air and operate in winter literally like it's summer. Now there's an effluent pump, and I'll get to the effluent pump after this. No savings, but an ability to shift the energy use. The barn fans here, we can see that reduction in use. Again, we can have the timer to reduce the peak demand. We're just dealing with the net energy use, but the peak demand is an important cost as well. The bore pump here, that we had the 30-second timer showing it was coming on and off, and you've got a leak in the pipe. I mean, that's almost a 50% reduction. And in that instance, it's a significant 50,000 kilowatt hour a year benefit to the farmer. A few other small savings there towards the right-hand side, 3 from the right-hand side. We've got the hot water in the line wash. Now that's close to an 80% reduction, because that hot water system previously had an electric element. When you have a heat exchange unit that's connected in line with the refrigeration system, the refrigerant travels through and uses that effectively as a condenser. It's almost free energy, so significant reduction in hot water use, as well as the hot water system for the milk vat clean, which is to the right there, where you just install a heat pump hot water system, given it's up to 80% more efficient than a standard residential system, which was what was currently being used. So significant energy savings across all equipment types. I've mentioned this effluent pump, not necessarily a per kilowatt hour saving, but with a new dam, there was the ability to actually shift the use in the middle of the day, given we've just for the moment been talking about energy efficiency. What that means is we're talking about changing the time of use profile through efficiency to then squeeze all the use into the middle of the day, so you can really use solar energy to derive the most benefit. So in this scenario over here, we have this green has been reduced, and there used to be heaps of green here after hours. So with that saving and pushing bore use into the middle of the day, we don't have after hours use that we couldn't actually address with solar energy, where the solar energy is generated in daylight hours. With the effluent pump, now that we have the scheduling information and looking at how we can do that in the middle of the day, we're increasing middle of the day use, which is beneficial for solar. And I'd mentioned before we had 120 kilowatt peak demand. Now between some of this fan switching, some of that reduction in bore usage, some of the refrigeration demands being reduced through shifting the roof up, and some of those timers on the cycling pumps, we've saved another 20 kilowatts of demand, which you're otherwise charged for. And here you can see a significant reduction in the hot water requirements given the hot water heat recovery. So the main message about efficiency here is it's not only about the net amount of electricity used, but it's about the time that it's used and using what we call load shifting. And you load shift to best match your load profile and create it as efficiently as possible so that you don't overcapitalize on solar energy. Now, solar is a lot more expensive than energy efficiency typically. The payback's longer. And in this scenario, you can see a 10 kilowatt system, a 20 kilowatt system, and a 30 kilowatt system. And here we've got the morning and the afternoon milking. And this in blue here is what's offset by solar. With the pink there showing what's fed into the grid. So you're capturing 91% of your site usage. We call this utilization. In the middle scenario, it looks about 50-50, but it's about 64% is used on site and 36% is exported to the grid. This one's way too big. It's 48% used and about 50-50 used and exported to the grid. Now, given that you're offsetting your use and that's your highest return on investment, it's all about maximizing the blue area, not caring so much about the pink, given it's disproportionately more valuable to offset your own use. But through all these energy efficiency measures, we've optimized and reduced our use and then scheduled loads in the middle of the day to create effectively a better return on investment, really leveraging energy efficiency, which is a lot cheaper commonly because they're just simple fixes. Raise the roof, fix the leak, put a bit of new cabling in so you're not turning all the fans on at the same time. If we think of that chart from the beginning and the electricity generation and the 2/3 loss on the right-hand side, why would you want to focus exclusively on renewable energy effectively just powering waste? So the actual location can also be matched to the load profile. I've mentioned the morning and afternoon milking. Here in green, we have an east array. In the orange, we have a west array. And in the blue, we have a north array. Now, while the peak generation might not be as high, having an east and west array with different parts, east and west, really does actually match a dairy load profile. So perhaps not locating your system north and considering the orientation, whether it's roof mounted or ground mounted, great opportunities to then optimize solar for your actual load profile. And perhaps do that after 12 months once you've done the efficiency so you can see the true potential. Now, coming back to this case study, we'd had someone that had an initial contract signed for 330,000 for a 200 kilowatt system. And it was quite staggering what the value proposition in this opportunity was and what's the benefit of investing in an energy audit. So in this scenario, from a financial perspective, it was 330,000 upfront for the solar system at a 200 kilowatt scale. that would save 31,200 in year one based on current ergon energy pricing. And over 15 years, that would have a 7% return on investment. If we actually look at a schedule of a smaller solar system, a 100 kilowatt system, and all these other amazing energy efficiency measures to make the load profile more efficient. And it includes the cost of a type 2 audit. We're looking at the 2,500 to just adjust the roof. We're looking at the cost for rewiring the barn fans. Here's a $50 timer for a pump. We actually had $15,000 more savings with $129,000 less spend. And the return on investment over 15 years was 21%. So from a financial perspective, energy efficiency and renewables with an optimized approach and really diligent focus, capturing all the data, following the Australian standard, which is, in my opinion, best practice for performing these kind of decarbonisation projects. There's a real significant financial benefit, inclusive of the costs of the professional services and the auditing to actually get this done. So get an audit done because it really pays for itself multiple times. The summation of those benefits in this case study where we had a budget of 330,000, the contract moved from 200 to 100 kilowatt hours installed capacity. That then captures the forecast of the 21% return versus the 7%. The avoided upfront capital costs and the actual cumulative energy cost difference is nearly 300,000 between both options. And a simpler way of thinking about that is there's basically 15,000 in additional cost savings by spending 129,000 less, because you're not just going the big solar route, effectively using renewable energy to power inefficiency or waste. You're optimizing, you're considering an integrated design approach. And in this instance, the type 2 audit paid for itself for those savings 32 times over. So there's a definite return on investment for having the expertise and skill and methodology to try and define least cost path with best benefits realization. So it's not uncommon, and it's from the last program, 3 case studies here that had 38.7, 46.7 and 58.6% reduction in energy costs. Coming back to my first point, and transformation, taking a 20 grand energy bill to 10 grand isn't that impossible, but it starts with an energy audit, getting that access to leading expertise, helping address the strategic risks, fixing problems, identifying efficiency, targeting 15 to 35% reduction, where those additional savings quite often outweigh the audit costs. So if anyone has any questions, my email's here, our website's here. I think there's a fantastic opportunity in Queensland, as tens, if not hundreds of these audits have demonstrated, that we have a significant transformational efficiency opportunity, and we've just got to get on with the work, and the benefits are there. Thanks so much for listening, and I'll pass it back to Andrew now.
Ryan, thank you very much. That was absolutely fantastic, thorough as usual, and actually really liked the follow through of the explanation of the energy conservation measures into the return on investment and the comparison with solar, because it is something that people often jump to as an initial energy efficiency measure. But as you can see, as you've shown through your presentation, when you bundle it up with some other energy efficiency measures, there's probably some good measures there that people can do first, which in turn mean that a smaller system was provided, is required. So just a couple of quick questions that I might ask. I don't see any in the chat, but one I wanted to talk about that we often get asked about, and we've done quite a few energy audits through this program and through previous programs on dairies, is that the drop in consumption through the course of the day, and how that presents a challenge both from a peak demand point of view and also from the point of view of choosing an appropriate solar system. And you touched on it a little bit because you talked about load shifting the effluent pump into that time and possibly the bore pump as well. And also you identified some efficiencies with hot water through heat exchange or capturing waste heat from compressors. But also, I wonder if you could just talk quickly about the potential for using heat and cooling in dairies as storage, so that during the day, if you do have some solar, well, I mean, using water and heat and energy, so you can either pump water, warm a little bit of extra water, or cool a bit of extra glycol or water. Could you please comment quickly on that?
Yeah, for sure. So that systems thinking approach and looking at your sources of heat or cooling requirements is key. I might first explain one of the really simple measures for reducing refrigeration, which is plate heat exchangers. So using bore, rainwater, or dam water. Quite commonly, most dairies have a plate heat exchanger that when the milk comes in, you'll be able to match the ambient cooling water, which is, say it's 22 degrees, you'll typically be able to get that within 3 degrees. So the simple version is to just have a tank of water, and most dairies do this, where the milk comes out of the cow at 36 degrees, goes through this plate heat exchanger, and then might achieve 26 degrees before it goes to the milk vat and then gets chilled to 3.5 degrees. So that principle is understood. The key question is, if you can chill with a plate heat exchanger to within 3 degrees of the coolant, why don't you refrigerate for free or at low cost the actual water and put in a second plate heat exchanger? So that concept of having free ambient cooling to 26 degrees, you then take the 26 down to, through water or glycol, a lower temperature, and you're performing that cooling in the middle of the day. So it's definitely something that's possible. A key consideration is the system losses. What percentage of system losses are there for storing that energy? So the tank, needs to be insulated. Don't just put it in any old tank or a concrete pit in the ground. Make sure that there's an efficiency in the actual storage. Although it's an apt point, as you pointed out, that because there's excess solar, it can otherwise be free refrigeration. And I've seen that be with evaporative cooling towers as well, which is lower cost than, say, for instance, refrigeration plant that operates in the middle of the day. So another nuance key to that is actually having the control logic. So it's operated when there's excess export. So a set of current transformers measure, hey, you've actually got free energy that's flowing to the grid. Like, do you actually have the ability to not turn that system on in a cloudy day so that it's not free energy? And there's a case study on the QFF website about just that, what the benefits are, and it relates to increased utilization of the solar essentially. But probably the final point is that not all energy use on the cold component is refrigeration, and I'm quite often surprised by the summation of small grain milling motors and other motors where with these 20 runtime counters, it really is death by small cuts, and that pie chart for refrigeration, intuitively isn't as big as you think it is. And hot water is a big part of that. So that ability to use a heat pump, some of the heat pumps from Apricus, for instance, have basic logic that says turn on between this time or this time. And some of the more advanced heat pumps for hot water systems, thinking of this heat storage, can actually communicate with solar, where you've actually got export energy. There's some logic to say, okay, heat the water now or don't because the solar's running or it's cloudy. A little bit more expensive, about a couple of grand difference for a residential scale heat pump. So I think it's an opportunity. You just really need to manage it and monitor it and know what you're doing. And that can all be addressed through an audit. I hope that wasn't too nerdy an answer.
That's perfect. And the other, it sort of made me think of another thing, which is the ability to real-time monitor energy consumption on site, and particularly farms that get solar systems can access data in real time from the inverter system, but also getting a meter put in at the same time that allows them to see their energy consumption on the same screen as their solar generation means that they can do what you're talking about, which is try and optimise your consumption during solar hours. And then you can get, you just do one with all of your energy, but you can get finer and finer grain, so you can put real-time meters on individual pieces of equipment or groups of equipment.
And that's a key constraint and why the audit methodology is valuable. With 20 runtime counters supported by spot measurements of electrical end use, if it's from an installed perspective, not including the ongoing subscription, if it's $2,000 a point, you wouldn't necessarily spend $40,000 to monitor 20 things, whereas the audit at a significantly lower cost provides that measurement for a month, because quite often it's the things like these bore pumps turning on and off, like it's 80-20 rule. You get 80% of the benefit from the first 20% of input up front in the first month. It's all systems that are legacy, that are inefficient, motors that are broken, high power factor. It's really front end in terms of the benefits from smart metering up front. So that's why an audit with the right data logging solves a lot of that problem. And then over time, the best monitoring is just having that communications with the solar portal. So often seeing that installed but not commissioned, it's a key question. Do you have that do you have the login? And then also just so many systems that are just offline, frustrating, but not uncommon, right?
Yes, we see those quite commonly too. And one more question, just some detail about one of the very first energy conservation measures you talked about. We do see outside dairy lots of those condenser units outside. They tend to be a bit forgotten because they're at the back of the cold room or at the back of the shed. It is important to shade them, isn't it, to protect them from the direct sun and the dust, but yeah, a bit of regular maintenance, get the roof up a bit higher, but also you need to manage airflow, keep dust off them. Even though they're around the back, you do need to do some regular maintenance on those things, Ryan.
Definitely, and the rule of thumb is a 5 to 15% improvement in performance through cleaning the condenser. So whenever your fridgie comes out, get them to clean it. I think 8 out of 10 aren't clean when I do an audit, and most of them aren't in direct sun, but that's a good point as well. It's maintain your equipment so it can work for you. It's not only the cost savings, but the effective asset life, where thinking of these non-energy benefits, like what is the detriment to the organization if your compressor blows up? Like how many milkings you're going to miss out on, and how do you maintain your equipment to reduce risk? So it's equally cost savings, but also just standard risk mitigation to just have efficient and well-maintained equipment generally.
Excellent, thank you. Well, thanks again for your presentation. That was great. It was in a good amount of detail, so it was really showed some of those potential, and yeah, it's great to have that return on investment information as well. So I'll just close by talking about a couple of the other things that we have for people on the Queensland Farmers Federation energy programs at the moment. We have the Queensland Ag Energy Hub. It's an online resource for farmers with all things energy. So this webinar will in fact be up there in a couple of weeks' time. But we have over 100 case studies. We've got fact sheets. We've got top efficiency tips by sector. There's details on energy programs and when they're available, grant programs. And it's very searchable. So if you're a dairy farm, or if you're a horticulture farm, or you're in the Burnett or Mareeba, you can search by where you are, what sort of technology you're looking for, and all those kind of things. So feel free to have a look at that. We also do an EnergySQ program, which is not quite as detailed an energy audit, but nevertheless a good energy assessment and a walkthrough assessment. And we do some carbon advice, and Jonathan Mendez online is one of our key people on that, along with Samuel Laffer, working with farms. And we're working with 100 farms in those 6 local government areas of Southern Downs, Gundawindi, Western Downs, Toowoomba, Lockyer Valley and Scenic Rim. So we're inviting farms to participate in that free program where we'll give you that initial energy assessment. We are doing 5 more of these webinars, and Ryan's up again this time next week, the 15th of October at 12 o'clock to talk about cold rooms. It's a very good segue from dairy into cold rooms because, you know, refrigeration is a big part of dairies as well as a lot of horticulture and other sectors. We're hoping to do one on piggeries, and we'll keep you posted on the timing for that. We're doing one at the end of October with Phil Zabo of the Saturn Engineering Group on large pumps. We're talking to Stephen Suter, who you may remember from a microgrids webinar we did a couple of years ago, talking about scheduling energy consumption. And then at mid-November, we're talking to Alan Day, Tailored Energy Solutions in North Queensland, about aquaculture and some of their findings from a couple of aquaculture farms up there, but with some very relevant information about voltage, power factor and variable speed drives that are relevant to all sectors. We also have the Energy Information Service for landholders. The Queensland Government worked with us to put this program together following the successful delivery of the Queensland Renewable Energy Landholder Toolkit. So farms or landholders from across Queensland can ring us with energy-related questions, and we'll do our best to answer them. And they can be anything from tariffs, energy efficiency, through to questions about negotiations with renewable energy developers or renewable energy zones or transmission. Really, any energy-related question we'll be able to talk to you about and hopefully help with. That's about all, and I think we've managed to wrap up in time, which is great. And once again, thank you very much to Ryan Dillon for providing all the expertise for today's session. Thanks again to Jonathan for being the guy for EnergySQ and helping us with the webinar as well. And look forward to catching you at the next webinar on the 15th of October at 12 p.m. Thank you, everybody.